Mechanics Part 2, which is Dynamics. And in this mini lecture, we're going to look at a quick introduction, and we're going to begin with the kinematics of a particle, and we're going to specifically focus on rectilinear kinematics, continuous motion. So looking at the picture that I have up of the rocket, sometimes the motion of really large objects such as this object, this rocket, or even an airplane, or even a car that you drive, they can be analyzed as if they were particles. So we're going to understand why we can do this. And then also we want to ask, if we measure the altitude of this rocket as a function of time, how can we determine its velocity and acceleration? So we'll come to this understanding in just a bit. The next application, okay, will be this sports car, this really fast sports car, and it travels along a straight road. So our question is, can we treat the car as a particle? If the car accelerates at a constant rate, we ask, how can we determine its position and velocity at some instant? And we'll develop this understanding throughout this section and throughout this course. So very quickly, an overview of mechanics. An overview of mechanics. So what is mechanics? By now you know that mechanics is the study of how bodies react to the forces acting on them. And in mechanics, you have statics, which is the first course that you've taken before this course. And it's just the study of bodies in equilibrium. And then there's this course that we're in now is dynamics. Dynamics covers two parts. Kinematics, which is concerned with the geometric aspects of motion, and kinetics, which is concerned with the forces causing the motion. So let's take a look. So we have a particle, and this particle, let's say, travels along a straight line. And this is a straight line path defined by the coordinate axis x. I'm sorry, s, coordinate axis s. All right, so let's take a look. Here we have s, and we're shown the position. And then the position of the particle at any instant relative to the origin, which we'll call O down here to the left, it's defined by the position vector r, or the scalar s. Scalar s can be positive or negative. And then typical units for our position vector r and the scalar s are meters or feet. Meters or feet. So then we have the displacement, right? That's shown at the bottom right diagram. The displacement of the particle is defined as its change in position. Its change in position. And we have vector form, delta r is equal to r prime minus r. We also have scalar form, which is delta s is equal to s prime minus s. So the total distance traveled by the particle is a positive scalar that represents the total length of the path over which the particle travels. Next is velocity. Velocity. So velocity is a measure of the rate of change in the position of a particle. So it is a vector quantity, right? A velocity has both magnitude and direction. The magnitude of the velocity is called speed, with units meters per second or feet per second. So the average velocity of a particle during a time interval, let's say delta t, is v sub average delta r over delta t. The instantaneous velocity is the time derivative of position, which is going to be v is equal to dr dt, that time derivative of position. So the speed is the magnitude of velocity, the magnitude of velocity. So v is equal to ds dt. And then the average speed, the average is distance traveled divided by elapsed time. Total distance traveled divided by elapsed time. So we can say v sub sp average is equal to, we said again, it's the total distance traveled divided by elapsed time. S sub t divided by delta t. Total distance traveled divided by elapsed time. Okay, so now we have acceleration. Acceleration. So acceleration is the rate of change in the velocity of a particle. Acceleration is the rate of change in the velocity of a particle. It's a vector quantity. Acceleration is a vector quantity. So the typical units in acceleration are meters per second squared or feet per second squared. So the instantaneous acceleration is the time derivative of velocity. It's the time derivative of velocity. So the vector form is a is equal to dv dt. However, then we have a scalar form. The scalar form is a is equal to dv dt, which is d 2s dt squared. All right, so acceleration can be positive, right, meaning the speed is increasing, or it can be negative, the speed is decreasing. And as you can see, the derivative that most texts will show, the derivative equations for velocity and acceleration can be manipulated to get a ds is equal to v dv, right? A times ds is equal to v times dv. Here's a summary of kinematic relations in rectilinear motion. So what do? We differentiate position, right? Differentiate position to get velocity and acceleration. So we have v is equal to ds dt, a is equal to dv dt, or we get right a is equal to v dv ds. All right, so differentiate the position to get velocity and the acceleration. All right, and then we integrate acceleration for the velocity and position. Integrate acceleration for velocity and position. So it makes sense, right? According to our calculus. So velocity is going to be, we're going to take the integral VL to V dV, which says go from 0 to T A dt, or from V0 to V dV, we say from SO to S, integrating ds. All right, and then the position is the integral ds SO to S is equal to integral V dV from 0 to T. Let's see. Oops, let's clean with respect to T. All right, so note that the initial SO and VO, that initial SO and VO represent the initial position and velocity of the particle at t equals 0. So again, that SO and VO represent the initial position and velocity of the particle at t equals 0. So here we have constant acceleration. So the three kinematic equations can be integrated for the special case when acceleration is constant, right, where a is equal to a sub c. And this is to obtain some very useful equations. So a common example of constant acceleration is gravity, right, i.e. a body freely falling downward toward Earth. That's a common example. So in this case, a sub c is equal to what we usually call g, right? G is just 9.81 meters per second squared, or 32.2 feet per second squared downward. All right, so here are the equations. So here are the presented equations. So in our first example, we are given a particle travels along a straight line to the right with a velocity of v is equal to the quantity of 4t minus 3t squared meters per second, where t is in seconds. Also, s equals 0 when t is equal to 0. We're told to find the position and acceleration of the particle when t is equal to 4 seconds. So first we have to do some planning, right? So our plan should be to establish the positive coordinate s in the direction the particle is traveling. Since the velocity is given as a function of time, then what do? We take the derivative of it to calculate the acceleration. We use our calculus. Conversely, we integrate the velocity function to calculate the position. All right, let's look to it. So first, we take the derivative of the velocity to determine the acceleration, right? Take the derivative of the velocity. So that's dv dt. So that's going to be d 4t minus 3t squared. All right, dt. And then that's going to get us what? Let's look at our calculus. We get 4 minus 6t. 4 minus 6t. T is equal to, when t is equal to 4 seconds, right? We're finding this answer when t is equal to 4 seconds. So that means a is equal to negative 20 meters per second squared. So I'm just plugging in that 4, right? 4 seconds in for t. 6 times 4 is 24. So 4 minus the 24 is negative 20 meters per second. All right, so negative 20 meters per second squared, or in this direction going to the left when t is 4 seconds. Okay, and now our next part is to calculate the distance traveled in 4 seconds. We can do this by integrating the velocity using um, SO equals 0, right, where t is equal to 4 seconds. So we have velocity is equal to ds dt, right, and that'll be s is equal to v t, okay, and then that can be the integral of ds going from SO to S. It's going to be equal to from 0 to t of the integral 4t minus 3t squared, right, dt. All right, and then from that we have s minus so is equal to, what do we get here? We get 2t squared minus t cubed, right? So I just integrated the 4t and the 3t squared. I used the addition, subtraction principle of integration and just integrated those two terms separately to get 2t squared minus t to the third. All right, so s minus, right, s sub 0, s sub o is 0, and that's equal to 2. And remember, t is equal to 4 seconds. So 2 times 4 squared minus 4 cubed. And then that should get us s is equal to negative 32 meters, or in the direction going to the left.